In this video, we're going to consider a quantity known as the discriminant of a quadratic function, which we'll see is equal to b squared minus 4ac, where a, b, and c are the coefficients of the quadratic function in standard form. And we're going to see what they tell us about the number of x-intercepts of the parabola associated with a quadratic function, or the number of solutions of a quadratic equation. So first, let's remind ourselves that a quadratic function, or a parabola, can have 0, 1, or 2 x-intercepts, depending on its vertical translations. For example, if we start with y is equal to x squared, like this, that has one x-intercept here at the origin. That's the same as solving this equation. We replace y with 0, and we get 0 is equal to x squared to solve for the x-intercepts, and the solution to that is simply x is equal to 0, which is right there. So x is equal to 0 is our x-intercept, and there's only one x-intercept for this function. If we were to move this down a bit, like so, we could get the function y is equal to x squared minus 1 by vertically translating it down 1. And we can see that it has two x-intercepts in this case, and we would find those by solving the equation where we set y equal to 0. We get 0 is equal to x squared minus 1, move the 1 over, 1 is equal to x squared. And if we square root both sides, remembering to take the plus or minus, we get plus or minus 1 is equal to x. And x is equal to 1 is here, and x is equal to negative 1 is over here. The two x-intercepts are 1 and negative 1. The two solutions to this equation are 1 and negative 1. Now let's go back to our parent function parabola and move it up by 1. Now we get y is equal to x squared plus 1, and we can see that because the parabola is opening upwards and because we've translated it up, there are no x-intercepts. And we can also see algebraically that if we replace y by 0 to find the x-intercepts algebraically, we would need to solve this equation. Moving the negative 1 to the other side, we get negative 1 is equal to x squared, and that's where we run into trouble, because if we square root both sides, we would get x is equal to the positive or negative square root of negative 1. And the square root of a negative number is not a real number, so this does not have a real number solution. So we can see that parabolas can have 0, 1, or 2 x-intercepts, and that's the same as saying that a quadratic equation can have 0, 1, or 2 real number solutions. If we restrict our solutions to real numbers, that is numbers that don't have square roots of negatives in them, then these are our options. We can also see that the quadratic formula sort of hints to us that this is going to happen, because the quadratic formula has a square root in it already. And you can imagine that if a, b, and c are such that b squared minus 4ac, the thing under the square root sign, is positive, then we won't run into any problems. Similarly, if this is 0, we won't run into any problems. But if b squared minus 4ac ends up being negative, then we're going to be trying to take the square root of a negative number, which we can't do and get a real number answer. And we'll look at this in more depth in a moment. To illustrate further, let's find the x-intercepts of each of these parabolas. So we start with y is equal to x squared plus 4x plus 3, and we're going to set y equal to 0 to find the x-intercepts. This function factors easily, so I'm going to factor it and get x plus 1 and x plus 3. That means that the x-intercepts are going to be negative 1 or negative 3. And if we think about graphing the parabola, we know it's opening upwards, and it's got x-intercepts of negative 1 and negative 3, so it's going to look something like that. Now this was easy to do using factoring, but to illustrate the point I'm going to be making, I'm going to do the same thing by using the quadratic formula. So I'm going to start from here, and I'm going to use x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. A here is 1, b is 4, c is 3. So I plug those in, and I get x is equal to negative 4 plus or minus 4 squared minus 4 times 1 times 3, all over 2 times 1, which is 2. And I get x is equal to negative 4 plus or minus, this is going to be 16 minus 12, which is 4. So the square root of 4 over 2. Which is equal to negative 4 plus or minus 2 over 2, which is equal to negative 4 plus 2 is negative 2 over 2, so that's negative 1, or, and then I get negative 4 minus 2 is negative 6 over 2, negative 3. So you can see I get the same answer. Now the reason I've done this is to show that what's happened here is I've ended up with the square root of a positive number. And let's watch what happens as we go through the further examples. In the next one, I've got a very similar looking quadratic function, except for the c value here is increased by 1. That means that it's the same as this parabola, but moved up by 1. This one's still going to be easy to factor, so to find the x-intercepts, I can do this. And this is a perfect square trinomial, which is going to factor like this. Or if you prefer, you can write it like x plus 2 all squared. Therefore, x is equal to negative 2. That means we've only got one x-intercept, and it's at negative 2. So the parabola is going to look like this, with the vertex on the x-axis. And any quadratics that can be expressed as just perfect square trinomials are going to have their vertex on the x-axis and have a single x-intercept. To do this using the quadratic formula, again, however, the only thing that's changed now is the c value. So everything looks the same, except for when I get to the c value, my c value is now 4, and that's over 2. Notice that what happens now is that I get 16 minus 16 inside the brackets, so I get negative 4 plus or minus the square root of 0 over 2, which is just the square root of 0 is 0, so I get negative 4 over 2, which is equal to negative 2. The important thing here is that b squared minus 4ac, this thing inside underneath the square root sign, ended up being 0, and so plus 0 and minus 0 end up being the same thing, and instead of having two different answers, it's collapsed down into one. Let's look at one more example. Now I've added one more to the c value. By taking this function and adding one more, I'm vertically translating it 1 up. And now to find the x-intercepts, I'm going to do this, set y equal to 0, and this one doesn't factor nicely because I can't find two numbers that multiply to 5 and add to 4. So I'm going to do it using the quadratic formula. X is equal to, again, the only thing that's different is c, so I get negative 4 plus or minus 4 squared minus 4 times 1 times 5, all over 2 times 1, which is 2. And now I get negative 4 plus or minus, I get 16 minus 20, which is negative 4 over 2. And now we've run into a problem because I can't take the square root of a negative number and get a real number answer. Therefore, there's no solution. If there's no solution to this quadratic equation, that means that this has no x-intercepts. And that makes sense because we said we've moved this up one more. So we're going to have something that looks like that. So you can see then that what's going on underneath the square root sign, that quantity b squared minus 4ac, is important in figuring out how many x-intercepts a quadratic function has, how many x-intercepts a parabola has. And that value, b squared minus 4ac, is called the discriminant, and sometimes it's given this symbol delta, which looks like a triangle. So delta, the discriminant, is equal to b squared minus 4ac. Just calculating this is enough to tell us how many x-intercepts we're going to have. So because of its place in the quadratic formula, this value, b squared minus 4ac, the discriminant, tells us the number of x-intercepts the parabola will have, or the number of real roots that the quadratic function will have. If b squared minus 4ac is greater than 0, then this number evaluates to a positive number, and we can take the square root of it and get a real number answer. Then, in evaluating the whole quadratic formula, we'll get two different answers, negative b plus whatever this square root is divided by 2a, and negative b minus whatever this square root is divided by 2a. So that will give us two x-intercepts for the parabola, or two real and different or distinct roots for the quadratic formula. Distinct is a mathematical way of saying different. So that could be something like this, where we have two x-intercepts, or if it's opening downwards, then we'd need the vertex to be above the x-axis like that. Both of these are examples of having two distinct real roots. If b squared minus 4ac, the discriminant, is equal to 0, then the square root of 0 is just 0, and plus 0 and minus 0 are the same thing, so this collapses and we get negative b over 2a as our only answer. So that's only one x-intercept. Now, you'll sometimes see that written as one real root, but you'll also sometimes see it written as two identical real roots. Those mean the same thing. It's as if you were taking this parabola and shifting it upwards and watching the two x-intercepts come closer and closer together until at the point when you had the vertex on the x-axis, they were superimposed. So one real root and two identical real roots mean the same thing. They mean that you've got a parabola that looks like one of these. Again, you could imagine that as being just one point, or you could imagine that as you were sliding this up from here to here, the points are getting closer and closer together until they're superimposed on each other. Either way, when b squared minus 4ac is equal to 0, you've got one x-intercept. Lastly, when b squared minus 4ac is less than 0, we saw that you run into trouble because you can't evaluate the square root of what is now a negative number, and so you get no solution when solving for the x-intercepts. So that's no x-intercepts, or 0 x-intercepts, and that means there are no real number solutions to the associated quadratic equation. And that's, as we saw, a situation where you have something like this, or it could also be something where the vertex is below the x-axis and it opens downwards. Let's look at a couple of examples. Without solving fully, find the number of real solutions of this equation. Now the first thing we want to do, as usual, is move everything to one side, leaving the other side 0. So if I do that, I get 3x squared minus x plus 1 is equal to 0. And I don't actually need to solve for x because I'm not being asked to solve fully. I'm just being asked to find the number of solutions there would be if I solved. So this is a discriminant question because if I figure out what the value b squared minus 4ac would be, I can figure out how many answers I would get out of the quadratic formula without actually having to go through and use it. So we want to evaluate the discriminant. Delta is equal to b squared minus 4ac. So in this case, a is equal to 3, b is equal to negative 1, and c is equal to positive 1. And if I just plug those in, b is negative 1 squared minus 4, a is 3, and c is 1, then I get 1 minus 12, which is equal to negative 11. So the discriminant, what would go under the square root sign in the quadratic formula, is negative. That means that I'm not going to be able to take the square root of that and get a real number answer. Therefore, there are no real solutions to this quadratic equation. And that's because the discriminant is less than 0. If I evaluated this and found that the discriminant was 0, I would have one solution. And if I found that the discriminant was greater than 0, I would have two real solutions. Let's look at another common type of question. We're asked to find the value of an unknown k for which this equation would have two identical real roots. And remember, we said that's the same as saying one real root. And that means that the discriminant has got to be equal to 0. So again, I'm going to move everything to one side. I get x squared plus 6x plus k is equal to 0. And now, for this, a is equal to 1, b is equal to 6, and the c value is actually equal to k. It's still an unknown. But in order to have two identical real roots, or one real root, we've said we want the discriminant to be equal to 0. In other words, b squared minus 4ac is going to be equal to 0. And if I plug a, b, and c in here, I'm going to have only one unknown, and I'm going to be able to solve. In other words, we said b is equal to 6, so I get 6 squared minus 4 times a is 1, and c is k. And that all has to be equal to 0. The discriminant has to be equal to 0 in order to get one real root, for that whole square root thing in the quadratic formula to disappear and to end up with only one answer. So now I just simplify this. I get 36 minus 4k is equal to 0. 36 is equal to 4k. Dividing both sides by 4, I get 9 is equal to k. And that's my answer. So if k were equal to 9, this would have become x squared plus 6x plus 9 is equal to 0. Factoring the left side, it's a perfect square trinomial, and we would get this. And you can see that this equation has only one solution, namely when x is equal to negative 3. So the important thing to recognize in these types of questions is that the question is telling you what to set the discriminant equal to. In this case, we wanted two identical or one real root, so we set the discriminant equal to 0. If this was asking for two distinct real roots, then we would have set the discriminant greater than 0. And if it was asking for no real roots, no solutions, then we would set the discriminant less than 0. So that's an introduction to the discriminant of a quadratic function and some typical questions.